For as long as humanity has existed, one question has followed us wherever we looked. Are we alone? It's a question older than science itself. Ancient civilizations searched for answers in the stars. Today, we search with space telescopes. The goal hasn't changed. Only the technology has. Over the past 3 decades, astronomers have discovered more than 5,000 planets beyond our solar system. Some are so hot that metal could melt on their surfaces. Others are frozen worlds drifting through endless darkness. Many are unlike anything we've ever seen. Each new discovery has brought us a little closer to understanding our place in the universe. But every so often, one planet captures the attention of scientists around the world. Not because it's another version of Earth, and not because anyone believes we've found alien life, but because it offers something far more valuable. A chance to study a world where the ingredients for life may exist under conditions we've never explored before. That planet is called K2-18b. Located about 124 light-years from Earth, K2-18b has become one of the most closely studied exoplanets ever discovered. Not because we visited it, not because we photographed its surface, but because, from over 100 light-years away, astronomers have begun reading the chemistry of its atmosphere. Using one of the most powerful space telescopes ever built, they've detected molecules that could help answer one of humanity's oldest questions. Not whether life exists, but where we should look for it. Today, we're traveling far beyond the planets we know to explore a world that may redefine the search for life in the universe. This is the story of K2-18b and why one distant planet has become one of the most important worlds we've ever discovered. Finding another planet sounds almost routine today. Hardly a week goes by without astronomers announcing a new discovery somewhere in our galaxy. But that wasn't always the case. For most of human history, the planets of our own solar system were the only worlds we knew. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Beyond them stretched countless stars. People wondered whether those stars had planets of their own. There was no proof, only possibility. That changed in 1992, when astronomers confirmed the first planets orbiting a distant pulsar. 3 years later came another breakthrough. In 1995, scientists discovered 51 Pegasi b, the first exoplanet found orbiting a sun-like star. It was a historic moment. For the first time, humanity knew with certainty that our solar system wasn't unique. The Milky Way was filled with planets. The challenge was no longer finding them. It was understanding what kind of worlds they actually were. As new telescopes came online, discoveries accelerated at an astonishing pace. NASA's Kepler Space Telescope transformed exoplanet science almost overnight. Instead of searching one star at a time, Kepler monitored more than 150,000 stars simultaneously. Its method was remarkably clever. Whenever a planet passed in front of its star, the star became ever so slightly dimmer. The change in brightness was tiny, often less than 1%. But by measuring those repeated dips with incredible precision, astronomers could determine that a planet was there. They could estimate its size, its orbital period, even calculate how much energy it received from its star. It was like detecting the silhouette of an insect flying across a distant floodlight. The planet itself remained invisible, yet its presence became impossible to ignore. Kepler revealed something scientists had long suspected. Planets are everywhere. Some systems contain tightly packed worlds orbiting closer than Mercury does to the Sun. Others contain giant planets larger than Jupiter. Some planets complete an orbit in just a few hours. Others take centuries. The diversity was astonishing. Instead of finding copies of our solar system, astronomers discovered something much more interesting. Nature builds planets in ways we had never imagined. Many of the most common planets in our galaxy don't even exist in our own solar system. Worlds larger than Earth, but smaller than Neptune. Planets wrapped in thick hydrogen atmospheres. Ocean worlds. Lava worlds. Even planets wandering through space without orbiting any star at all. The universe turned out to be far more creative than our early models had predicted. Among thousands of discoveries, astronomers face a new question. Which of these worlds deserved closer attention? Finding a planet is only the first step. The real challenge is deciding which ones might reveal something extraordinary. Most exoplanets are simply too difficult to study. They're either too small, too far away, or hidden by the overwhelming brightness of their parent stars. Only a small number pass directly between their star and Earth, allowing telescopes to analyze starlight as it filters through the planet's atmosphere. Those rare alignments give scientists a unique opportunity. Instead of seeing the planet itself, they study the fingerprints left behind by gases surrounding it. Every molecule absorbs light differently. Water vapor leaves one pattern. Methane leaves another. Carbon dioxide creates its own unmistakable signature. By separating starlight into a spectrum, astronomers can identify these invisible fingerprints from more than 100 light years away. It's one of the most remarkable achievements in modern astronomy. Without ever leaving Earth, we can begin to understand the atmosphere of another world. This technique eventually led astronomers to a planet orbiting a small red dwarf star in the constellation Leo. It wasn't especially famous at first. It wasn't the largest, or the closest, or even the easiest to observe. It simply appeared to be another promising exoplanet in an ever-growing catalog. That changed in 2015. Using data collected by NASA's K2 mission, the extended phase of the Kepler Space Telescope, astronomers confirmed the existence of a planet now known as K2-18b. At first glance, it seemed to occupy an interesting position. It orbited within the star's habitable zone, the region where temperatures could allow liquid water to exist under the right conditions. That single detail immediately attracted attention. But scientists knew better than to jump to conclusions. Being inside the habitable zone doesn't automatically make a planet habitable. Venus lies near the inner edge of our own sun's habitable zone, yet its surface is hot enough to melt lead. Location alone tells only part of the story. To understand a planet, scientists need to know what surrounds it, its atmosphere, its chemistry, its climate. For several years, K2-18b remained an intriguing candidate. Then, in 2019, observations from the Hubble Space Telescope revealed something extraordinary. Astronomers detected evidence of water vapor in its atmosphere. It was the first time water had been identified in the atmosphere of a planet orbiting within the habitable zone of another star. The discovery made headlines around the world, not because scientists believed they had found life, but because they had found something every known form of life on Earth depends upon: water. It was a major step forward, yet it also raised even bigger questions. How much water was there? Was it floating above a deep global ocean, or suspended in a thick atmosphere over a planet unlike anything in our solar system? No existing telescope could provide the full answer. The evidence was promising, but incomplete. Astronomers needed a more powerful instrument, one capable of reading an alien atmosphere in far greater detail. That instrument had already begun its journey into space. Its name was the James Webb Space Telescope. By the time the James Webb Space Telescope began observing K2-18b, astronomers already knew one thing: this wasn't another Earth, but it wasn't another Neptune either. Instead, K2-18b appeared to belong to a category of planets that doesn't exist anywhere in our own solar system. That realization opened an entirely new chapter in planetary science. Because before scientists could ask whether life might exist there, they first had to answer a much simpler question. What kind of planet is K2-18b? At first glance, the numbers seem confusing. K2-18b is about 2.6 times wider than Earth and roughly 8.6 times more massive. That's far too large to be considered an Earth-sized planet. Yet it's also much smaller than Neptune. For decades, astronomers had no equivalent planet close enough to study. Our solar system jumps almost directly from rocky worlds like Earth to ice giants like Uranus and Neptune. But beyond our solar system, this missing category turns out to be remarkably common. In fact, planets like K2-18b may be among the most abundant worlds in the Milky Way. Ironically, the type of planet we know the least about may also be one of the most common in our galaxy. Understanding K2-18b required scientists to think differently. Instead of asking whether it looked like Earth, they asked what its internal structure might be. Several possibilities quickly emerged. Perhaps it was a giant rocky planet with an unusually thick atmosphere. Perhaps it contained vast amounts of water beneath layers of gas. Or perhaps it represented something entirely new. As computer models improved, one idea began attracting serious attention. A Hycean planet. The name combines two familiar words: hydrogen and ocean. A Hycean world is thought to possess a global ocean hidden beneath a deep, hydrogen-rich atmosphere. Unlike Earth, where nitrogen and oxygen dominate the sky, the atmosphere above a Hycean ocean could be composed mostly of hydrogen, with smaller amounts of water vapor, methane, carbon dioxide, and other gases. If that picture is correct, K2-18b isn't simply a bigger Earth. It's an entirely different kind of habitable world. That idea changes the way we think about life itself. For decades, scientists focused their search on planets that looked as much like Earth as possible. Similar size, similar temperatures, similar atmosphere. The assumption seemed reasonable. After all, Earth is the only planet known to support life. But nature doesn't always follow our expectations. If Hycean planets truly exist, then habitable environments may be far more diverse than we once believed. Life might not require an Earth-like atmosphere at all. It might thrive beneath skies unlike anything we've ever experienced. K2-18b challenged one of the oldest assumptions in astrobiology. Maybe we've been searching too narrowly. If you could somehow descend through the atmosphere of K2-18b, the journey would feel nothing like entering Earth's sky. The upper atmosphere would likely be rich in hydrogen, the lightest element in the universe. Hydrogen behaves very differently from a nitrogen and oxygen we breathe. It retains heat more efficiently and changes how energy moves through an atmosphere. As sunlight from a planet's small red dwarf star passes through these upper layers, the gases absorb specific wavelengths of light. Those tiny changes are exactly what telescopes like James Webb Space Telescope measure. Astronomers don't see oceans directly. They don't photograph clouds. Instead, they analyze light that has crossed an alien atmosphere. Every observation is like reading a page from a book that no human can physically visit. Beneath those upper layers, conditions become far less certain. Some models suggest a deep global ocean stretching across the entire planet. Not scattered seas separated by continents, but one uninterrupted body of water spanning the globe. If that's true, K2-18b could be the closest thing we've ever found to a true ocean planet. There may be no mountains rising above the waves, no deserts, no forests, no continents at all, just an endless ocean extending beyond every horizon. Other models paint a different picture. They suggest the atmosphere could become so dense that pressure increases dramatically with depth, eventually forming exotic layers unlike anything found on Earth. At those extreme pressures, water may behave in unfamiliar ways, transitioning into phases that can only exist deep inside massive planets. The truth is that scientists still don't know which model is correct, and that's precisely what makes K2-18b so fascinating. Every new observation has the potential to eliminate one possibility and strengthen another. The star itself also plays a crucial role. K2-18b doesn't orbit a star like our Sun. Its parent star is a red dwarf. These stars are much smaller and cooler than the Sun, yet they make up roughly 3/4 of all stars in the Milky Way. Because red dwarfs produce less energy, their habitable zones are much closer in. K2-18b completes one orbit in only about 33 Earth days. That doesn't mean the planet experiences rapid seasons. Instead, it simply circles much closer to its star than Earth does to the Sun. Despite that close orbit, the weaker energy output of the red dwarf allows temperatures that may still support liquid water under the right atmospheric conditions. It's a reminder that habitability isn't determined by distance alone. The type of star matters just as much. Living near a red dwarf comes with challenges. Young red dwarfs are known for powerful stellar flares that release bursts of radiation into space. These eruptions can strip away planetary atmospheres over billions of years. They can alter atmospheric chemistry. They may even affect the long-term stability of liquid water. Whether K2-18b has managed to preserve its atmosphere despite these stellar outbursts remains an active area of research. Its thick hydrogen envelope may provide protection, Or it may simply represent the atmosphere that survived after billions of years of evolution. At the moment, scientists can't say with certainty. One of the most remarkable aspects of K2-18b is how little we actually know. That may sound surprising after decades of observations, but every major discovery has also revealed new questions. Is there truly a global ocean? How deep could it be? What is happening beneath the atmosphere? Could there be a rocky seafloor? Or does the immense pressure create entirely different layers deep inside the planet? Each possibility leads to a completely different picture of the world, and each requires new evidence before scientists can confidently choose between them. This uncertainty isn't a weakness. It's how science moves forward. Every observation narrows the possibilities. Every spectrum removes another piece of the mystery. K2-18b has already transformed our understanding of what a potentially habitable planet can look like. But the most important discoveries may still lie ahead, because understanding a planet's atmosphere is only the first step. The next challenge is even greater. Can chemistry alone reveal whether a distant world might support life? That question would soon place K2-18b at the center of one of the most exciting scientific investigations of the 21st century. For centuries, searching for life beyond Earth seemed almost impossible. Even if another inhabited planet existed, how could we ever know? The nearest stars are trillions of kilometers away. No spacecraft we've ever built could reach them within a human lifetime. So if we can't visit these distant worlds, we have to learn how to investigate them from here. That challenge has transformed astronomy into something remarkable. Today, scientists don't need to land on an exoplanet to study it. Instead, they study its atmosphere, because every atmosphere tells a story. When K2-18b passes in front of its parent star, a tiny fraction of the starlight travels through the planet's atmosphere before continuing toward Earth. Most of that light passes through unchanged. But certain wavelengths are absorbed by specific gases. Water vapor blocks one set of wavelengths. Methane blocks another. Carbon dioxide leaves its own unmistakable pattern. Those missing pieces of light create what astronomers call an absorption spectrum. It's essentially a chemical fingerprint. By measuring those fingerprints with extraordinary precision, scientists can identify gases in an atmosphere that no telescope will ever directly photograph. It's one of the greatest achievements of modern astronomy. We're learning the chemistry of worlds we cannot even see as tiny dots of light. This is exactly why the James Webb Space Telescope has become such a revolutionary instrument. Unlike Hubble Space Telescope, which mainly observes visible and ultraviolet light, James Webb Space Telescope was designed to study the universe in infrared wavelengths. Infrared light is especially valuable because many important atmospheric molecules leave their strongest signatures there. Water, methane, carbon dioxide, ammonia, each becomes much easier to detect. For exoplanet science, James Webb isn't simply a better telescope. It's a completely new way of studying distant worlds. Instead of asking whether a planet exists, scientists can begin asking what its atmosphere is actually made of. When James Webb Space Telescope observed K2-18b, the results immediately attracted worldwide attention. The telescope detected strong evidence for methane and carbon dioxide in the planet's atmosphere. Those molecules were important for several reasons. First, they supported the possibility that K2-18b could possess a hydrogen-rich atmosphere, consistent with the Hycean planet model. Second, they suggested a chemically active world rather than a simple ball of gas. And perhaps most importantly, they showed that James Webb Space Telescope was capable of analyzing the atmosphere of a potentially habitable exoplanet with unprecedented detail. The observations marked the beginning of a new era, not because they confirmed life, but because they demonstrated that studying potentially habitable worlds from over 100 light years away was finally becoming possible. Then came the molecule that captured headlines around the world, dimethyl sulfide, usually shortened to DMS. On Earth, dimethyl sulfide is primarily produced by living organisms in the oceans, especially microscopic marine phytoplankton. As these organisms grow and interact with seawater, they release DMS into the atmosphere. Because of that connection, DMS is considered a potential biosignature, not proof of life, but a chemical that could, under the right circumstances, point scientists toward biological activity. When early analyses of James Webb Space Telescope observations suggested the possible presence of DMS on K2-18b, excitement spread quickly. News headlines asked whether humanity had finally detected signs of life beyond Earth. It was an extraordinary claim, and extraordinary claims require extraordinary evidence. The scientific community responded with caution, not skepticism for its own sake, but because science advances by testing every alternative explanation before accepting an extraordinary conclusion. The signal suggesting DMS was weak. Additional observations were needed. Other molecules could potentially produce similar features in the spectrum. Instrumental noise also had to be carefully ruled out. Astronomers around the world began reanalyzing the data using different atmospheric models and independent statistical methods. This process is one of science's greatest strengths. Discoveries aren't accepted because they're exciting. They're accepted because they survive repeated attempts to prove them wrong. Even if future observations confirm the presence of dimethyl sulfide, the mystery wouldn't be over. On Earth, biology is the dominant source of DMS. But K2-18b is not Earth. Its atmosphere is different. Its chemistry is different. Its oceans, if they exist, would be unlike anything in our solar system. Scientists must also consider whether unknown geological or photochemical processes could produce the same molecule without life. This is why astronomers rarely use the phrase proof of life. Instead, they talk about multiple lines of evidence. One molecule is interesting. Several molecules forming a consistent pattern become much more compelling. Science builds confidence piece by piece, not all at once. The search for life has gradually evolved over the decades. At first, scientists focus on finding planets inside the habitable zone. Then they search for liquid water. Now they study atmospheric chemistry. The next generation of telescopes may go even further. Future observatories are expected to analyze smaller, more Earth-like planets with even greater precision. They may search for combinations of gases that are difficult to explain through geology alone. Oxygen and methane existing together, seasonal changes in atmospheric composition, or entirely new biosignatures that scientists haven't yet considered. K2-18b is not the final destination. It's one of the first major steps along that path. Perhaps the most remarkable part of this story isn't the planet itself. It's what it says about humanity. Just a few generations ago, we didn't know whether planets existed around other stars. Today, we're measuring the chemistry of atmospheres more than 100 light years away. That's an extraordinary leap in knowledge. And yet, every answer has produced even more questions. What lies beneath K2-18b's atmosphere? Is there truly a global ocean? How common are Hycean worlds? Could life emerge under conditions completely different from those on Earth? Or have we simply found another fascinating planet that challenges our understanding of planetary evolution? At this moment, we don't know, and that's exactly what makes this era of astronomy so exciting. The search for life has never been about finding a single planet. It's about understanding our place in the universe. Every new telescope extends our vision a little farther. Every new discovery reshapes the questions we ask. K2-18b hasn't answered humanity's oldest question. Not yet, but it has changed the way we search for the answer. It has shown us that potentially habitable worlds may come in forms we never expected, that oceans might exist beneath hydrogen skies, that distant atmospheres can be studied across unimaginable distances, and that the next great discovery may already be waiting in the light, reaching our telescopes tonight. Perhaps one day, astronomers will look back at K2-18b not as the world where we found life, but as the world that taught us how to find it. Somewhere among those stars, there may be another world waiting to be discovered, not because it looks like Earth, but because it reminds us that the universe is far more diverse than we ever imagined. Our search has only just begun, and with every new observation, the cosmos reveals another chapter of its story.